Okay, so welcome to part 4, where we're going to take a look at that idea of the derivative again, but we're going to take a look at it using an alternate definition, an alternate limit form. When I say an alternate limit form, that's literally what I mean. This is not a better, not a worse, just a different way to look at it. The different way to look at it is to look at it as, instead of defining the 2 points as c and c plus a little bit, define the 2 points as a fixed point c and a movable point when x is x. Then you have 2 points on the curve, c, f of c, which we would call our fixed point, right? So c would be a number like 3 or 5 or -7 or whatever. And then we have a second point on our curve, x comma f of x, and that point moves. So that's the point that we're going to move down the graph closer and closer and closer until it gets to that point C. And so as that is moving along the curve, essentially what we're doing is we are taking a limit as x approaches C. Now this picture here has been drawn to have the point x, f of x, to the right of point C, but there's nothing about the math that says that that point couldn't have started over here as x comma f of x and then move in that direction to C. It's just it's usually drawn to the right and moving to the left. Okay. You'll notice that this is just a different way to do what we've already done. This is a different way to find the value of the derivative. Okay. And why is it the value of the derivative? It's the value of the derivative because that point right there is a number for x, not a variable for x. Okay? So it's just a different way, a different limit. Right? Some people like this one better, some people like this one better. It just depends on which one you like better. Right? Both of them will get the job done. Here's what I will tell you from my experience with them. This definition is better if you like to distribute and then factor out your delta x. And this definition, where is it? Oh, here, is better if you like to factor and then cancel. So you'll be factoring and then cancel out things. Okay? It's just an alternate form of the definition. All right, so we've been talking about differentiability. We've been talking about where a function is differentiable or where it is not differentiable is what we need to get to. Right? So you said that if a function is differentiable on an interval, then it's differentiable on the open interval in between. But the question is, what would make something not be differentiable? So what is the relationship that exists between differentiable, not differentiable, and then a concept that we already know, and that is continuity? Right? So if we take a look at these 3 graphs right here, okay, I would hope that all of you at this point would say that this one is continuous, this one is continuous, but this one is not continuous. Okay? I want to be able to talk about where these graphs are continuous, but also I want to talk about where they are differentiable. Okay? All 3 of these graphs have issues with differentiability. Right? This graph has a problem right here, this graph has a problem right here, and this graph has a problem right here. Right? So even though the graph on the left, just for simplicity, I've got them labeled down here as A, B, and C. So graph A over there on the left has an issue with differentiability at that corner right there. And here's the problem. I'm just going to zoom in on this one first off. The definition says that if this thing had a derivative there, a value for that derivative, then that limit as delta x approaches 0 would exist of f of c plus delta x minus f of c divided by delta x. But the left-hand limit and the right-hand limit wouldn't be the same. And if we go way back, I'm talking like 2, maybe 3 weeks ago now, for a limit to exist, the left-hand limit had to be the same as the right-hand limit. But if you look at the slopes of these tangent lines over here on the left, these are all positive values. And so as we approach, that limit is going to be a positive number. Well, all of these tangent lines are negative values. And so as we approach with the right-hand limit, those would all be negative values. So this graph is going to have an issue at that point right there. That point is called a corner or a cusp, depending on, again, who wrote the textbook and how specific they want to be. But this is a function that is continuous on this entire interval, but is not differentiable at some value x equals a, because the graph has a corner or a cusp at that point. Right? This graph has an issue with differentiability. It is not differentiable, again, at x equals a, because there's something going on here. The graph is broken. So again, we're going to have an issue because the left-hand limit for those slopes of tangent lines and that right-hand limit for those slopes of tangent lines is not going to be the same. These aren't going to match up. And because that graph is broken and that left-hand limit and that right-hand limit for our derivative aren't going to match up, this thing is not going to be differentiable at that value x equals a. What's the issue here? Why does this one fail to be differentiable? Well, it's not differentiable there at a because the limit as that delta x approaches 0 of f of c plus delta x minus f of c divided by delta x. Right there at that point, that tangent line goes vertical. And if that tangent line goes vertical, what's the value of the limit? Well, the value of the limit does not exist because a vertical tangent line means that this limit is going to infinity, and infinity is not a number. Infinity is a concept or an idea. And since it goes vertical, it fails to be differentiable. Right? All right. So here's the relationship. This is the mathematical relationship between continuity and differentiability. If a function is differentiable somewhere, then it must be continuous there. So differentiability implies continuity. But it is possible for a function to be continuous and not be differentiable. Okay, so continuousness, continuity does not imply differentiability, but differentiability implies continuity. If you have ever studied logic, P implies Q is not logically equivalent to Q implies P. So differentiability implies continuity does not mean that continuity implies differentiability. All right, so this brings us to the end, but I wanted to do one example of the alternate definition for the derivative. The alternate definition for the derivative said that the slope of the tangent line could be found by taking the limit as x approaches c of f of x minus f of c divided by x minus c. So I'm going to make up a function. My function will be x squared plus 2x. That sounds good. And we will say that c equals 3. Okay? If c equals 3, what's f of 3 or f of c? So that's going to be 9 plus 6, that's 15. So plugging all of that information into my definition, I get that the slope of the tangent line is going to be equal to the limit as x approaches 3 of x squared plus 2x minus f of c 15 divided by x minus 3. Now this looks like a lot like those problems we were doing a couple sections ago. So I am going to try direct substitution. So if I use direct substitution, I'm going to get 9 plus 6 minus 15 divided by 3 minus 3, which is 0 divided by 0. 0 divided by 0 means somebody punched a hole in my graph. I need to do more. In this case, I'm going to factor. So then I get the slope of the tangent line is going to be equal to the limit as x approaches 3 of x minus 3 times x plus 5, just factor the numerator, divided by x minus 3. So what's this? Well, that's the 0 over 0, so we're going to ignore that and do direct substitution on what's left. And so I get 3 plus 5, or 8. So the slope of the tangent line to the curve at the point is 8. So what you'll notice is this definition works as well as the other definition, the delta x to 0, or the x to c. They work the same. They perform the same actions. It's just a matter of which one do you want to use. This one requires that you can do this step right here, and that is you can take this and factor it. So if you're good at factoring, or if your function is simple enough where you think the factoring should work easily, this is a better approach. As soon as your function gets ugly, though, then factoring is not a good approach, and the delta x to 0 usually works better. And what I mean by that, if your function doesn't look like it would factor easily, remember the one we did a while ago? Where is it? This one, right? This was a cubic equation, which means that when I get to the step of factoring, I'd have to be able to factor a cubic. How good are you at factoring cubics? Right? Me personally, I'm not very good at factoring cubics, so I don't want to factor a cubic. So I would not use the x to c approach. I would use the delta x to 0 approach. Right? This is not to say that the x to c would not work, but what it would require is something that I'm not good at, factoring a cubic. So I would stay away from that because I don't want to do something I'm not good at. I want to be able to get the job done in an efficient manner. All right, this brings us to the end of section 3.1. The next video will start with section 3.2, and we'll take a look at some more concepts, some more ideas, some more techniques for differentiation. Okay? See you all back here for 3.2.